computer. So new assignment, hangman, cheater's hangman. So how many of you did this with Professor Fiore?
I did.
Yeah, I also did it with Fiore.
He likes this assignment. So do I. And neither of us are saying, and neither of us are like, well, I'm going to drop this assignment. So we both give this assignment, but we do it in different ways because it's such a good assignment. Now, the thing is that, however, just because you've done it before doesn't mean it's going to be easier this time. Just means you understand what the concept is. So now with that said, for this one, you're going to be using hash tables. So in other words, you're going to be using the hash map data structure and the hash set data structure. Okay. So I doubt that you guys did that with Fiore because that's not something typically taught there. So I provide you with the PDF of my write-up of the assignment with some examples if you haven't seen the assignment yet. And then we've got words.txt. Okay. Which is so words.txt, by the way, you can see it's 399 kilobytes. It's actually quite the large file. It's actually the file you would see, let's see, in a, probably pull this up quicker. Oh, nope, it's already there. It's what you would see in a Unix system for spell checking purposes. Insufficient, interesting. Oh, I bet it's because I'm running folding at home. Yeah, you've been running all night. We can give the computer a bit of a break. How interesting. Interesting. Okay, whatever. I'm gonna try one more time just to show you, but if we can't, then mote it be. I've never seen that error before. Okay, so this is a file you'd find under user/sayer/dictionary or dict. And it is literally a dictionary of all the words in the English dictionary. And I do mean all the words, and that is a warning to you. It is all of the words in the dictionary. I can't possibly filter out all the naughty 4-letter words or all words that contain the 4-letter words, which is a great time to. And I mentioned this is because I had an unfortunate incident where a student had something embarrassing pop up while they were demoing this to a TA. So my suggestion is that don't run don't run this on 4-letter words. Now, because this is a dictionary and it contains every single word that would be recognized in the English language. Now, as to why I didn't remove this. First off, can everybody hear me? Making sure that everybody can hear me. And
Yeah,
we got you.
Okay. This is now a very good time to talk about a common problem in computer science, and that we all get to giggle about. So you can put on your 4th grader hats and kind of giggle. This is going to be in the. This is all about what's called the Scunthorpe problem. Give me 1 second. Scunthorpe problem. So for those of you who don't know, Scunthorpe is a town in North Lincolnshire, and what happened is that basically that the profanity filter for AOL prevented Scunthorpe from creating a account on AOL, America Online, one of the first early easy to use internet access services. Scunthorpe is a very nice town, but essentially it said, oh, this substring inside of this town, the substring inside this name is a dirty word. So we're not going to let you use it because the substring is an offensive word. So that made some issues. Google had this issue with safe search, which prevented people from searching for local businesses, right? So, right, if you search for something on Google, let's go with tacos. Tacos are fairly harmless, right? There's a setting for safe search, right? For high, and it used to be like safe search, where you would hide explicit, where basically you had like 3 settings, basically, so that which would prevent you from accidentally visiting something that you should not be visiting at work, right? But anyway, what would happen is that Google said, hey, Scunthorpe has this substring in it, so we are going to filter it so the people can't look up their own town's website now. Huge issue. Another issue, like, so this is not just because of that. So shitakemushrooms.com blocked by a filter because of obvious reasons. So here, Montreal Urban Community, its acronym in French, got blocked, right? Craig Coburn was unable to use his surname with Hotmail. Also, he had problems because his job title, software specialist, had the substring Cialis, which is often used in spam emails, right? So, if you have, so other people, Lipschitz, Wiener, those basically names can get blocked like that. This is a tough problem in computers. We can laugh all you want. I'm sure a lot of you are laughing behind the screens, right? But this is actually a really tough problem. Like, if you're a web admin, right, and you want to make it so that basically that you're filtering out some stuff, so that people can't access stuff at work, or people aren't going to be able to send spam things. How do you make it so that your services are not accidentally blocking people? You can't ask people to change their name. That would be so wrong. Right. Problems can occur with socialism, socialist, and specialist because of Cialis. Blocking of the word specialist is liable to block emailed resumes and CVs. Right? You send in it and saying, okay, yeah, I worked as a software specialist or some other kind of specialist, but software specialist makes sense for you guys, right? As a job position, like a legitimate job position you own, and it gets blocked because spammers use the substring to send out spam so that old people will fall for it and give them money, right? So these are a lot of so essentially these are like false positives in computer science. So it is a very hard problem to deal with. It's not something you have to solve for this class, I should point out. But I'm just trying to say this is why I don't really bother with this. Instead, I try to use it as a teachable moment to talk about a real life problem that actually has difficulties with it, right? I'm sure, I mean, even in like video games where you have people registering usernames, you will have the Scunthorpe problem, which will prevent you from using you might type in a username and it says that you can't use that username. Well, not because somebody else took it, but it's just got a banned substring. So that is a difficulty of the Scunthorpe problem. So hopefully you all enjoyed that without necessarily being felt too. Now I just gotta make sure nobody felt too uncomfortable during that, right? And if you did, you don't have to speak up. You can email me. If people are speaking, then they are muted. Did you feel you felt uncomfortable during that? Oh no, timestamp. That was 10 minutes ago. So unless you're precognitive, okay. So All right. So anyway, that was towards taking it with Fiore. Okay, got it. Okay. So now with regards to this problem, I plan on going in over this problem in more detail on Wednesday, but feel free to work on it. I've made it due on Thursday. Sorry, I've made it due next Wednesday, but the gist of it is that we are going to use hash tables and hash maps to do this problem. Okay. Oh, okay. Sorry. For some reason, I'm just having trouble remembering how to navigate this all. Back button. All right. So this PDF, by the way, notice that this one is worth 200 points versus 100. And also you can, just like the very first one, you can demo it with somebody else. So you can both get credit for the same code. I have different examples for this and how this works. And I will be going over more explicit examples on Wednesday once people have gotten a start for this. You definitely want to use maps and sets for this one to make it easier, because you want this to run fast, super fast. The entire point is that it should be completely undetectable for cheating. Now for those of you who've read ahead and been listening, what is the big O runtime for a hash map or a hash set? Anyone?
For the contains, I think it's O of 1 time.
That's right. It's actually O of 1 for everything. It is O of 1 for contains. It is O of 1 for add. It is O of 1 for remove. Everything is O of 1 for get and set for or get and put in the terms of for hash maps. So these so the hash map and hash maps are like basically our most powerful data structure that we have access to. Hash maps are amazing. Or hash tables, anything built with a hash table. They're also referred to in other languages by different names, by the way, I should mention. They are called associative arrays in some languages. In other languages, they're called hash maps. In other languages, they're called hash tables. And in Python, they're called dictionaries. In other languages, they're called dictionaries as well. So these are extremely powerful. These are extremely powerful data structures that do things in constant time. Usually, very rarely it will take them O of n time to do stuff. But most of these are very well designed, and so they will take constant time usually to do their operations. Except for when, like array lists, they have to resize themselves, in which case that's the only time it will take O of n. But we say that it is constant time amortized. In other words, it will be constant time for pretty much everything except for one operation out of like n operations. And that work just gets, on average, comes down to constant time. So now how does this happen? It happens because it happens because of a process of black magic we called hashing. But essentially what it involves is that we are going to be making a sacrifice of our memory to the gods of runtime to ensure that we have good, clean runtimes. Hash maps make a sacrifice for this constant time. So we saw with trees that we can, if our data is sortable, we can do stuff in log n time. We can put things in, we can put things in and get them out in log n time. And it'll be in sorted order. Right, trees sort by basically having something in the middle and then going left to right. Whereas heaps we saw would sort things by just keeping the smallest thing on the, it basically gives us a priority queue. It keeps the smallest thing or the biggest thing on top, right? And that doesn't, and unlike the tree, it doesn't let us find something, but it always lets us find the smallest thing, which is a different use case. So trees and heaps, these tree-based structures are all about log n time, keeping things sorted in some way, shape, or form. Hash maps and hash table, hash maps, anything, hash sets, anything built with a hash table, right? So a hash map and hash set, they're two different, they're hash-based implementations of maps and sets, which are the basic data structure. You can create tree maps and tree sets, as you'll see, but we'll be using the hash because they run in constant time. But they're all based off something called a hash table. Hash tables say order schmorter. I'm just gonna basically throw things wherever. I hope the order in which you put stuff into a hash table wasn't important to you. I hope that you weren't counting on me to keep things in order, because I'm not gonna. It's not worth it. Not worth the trouble. So that's the other sacrifices. You can't keep things in order there is no semblance of order in a hash table, and it uses up tons of extra memory, anywhere to 30 to 50 extra %. Just wasted space to make sure that it runs fast. Now, with our videos for the hash tables, what is relevant? Well, yes, all the videos are relevant, but you want to know what is the most relevant to know what you need to watch before you start. And for that, I'm more than happy to oblige. So, hash table videos. There are quite a number of hash table videos, but a lot of them are short. Here I talk about how to use sets in these first videos, how to use hash tables, or hash maps. Okay, so up through 10 is how to use those data structures. Up through and 11 and let's see, and then these are basically 11 through 14 is more of the theoretical underpinnings of how hash tables work. And then finally 15 through 23 is how you build these things from scratch. And I do build it completely from scratch, except for that one piece of black magic that I mentioned earlier. I don't create my own hashing function. I just go ahead and use Java's hashing function because that's black magic beyond the ken of mere mortals like myself. Not really, but it is tough stuff. So definitely these will be relevant for, so the first 10 videos are relevant for basically making sure that you can do what you need to do for the exam, which will not probably be, let's see when that will probably be. So exam, let's see. So let's be honest here. How does next week look for people? I heard projects were due. So how bad is next week?
I have an exam next week. But
Yeah, me too.
It's pretty bad.
Yeah,
it's like wave 2.
Sam's.
All right. So would people be more comfortable with me? Would people be okay with taking an exam the first week of November?
Yes.
Yeah.
Sure.
All right. We'll do the first week of November. When? Don't know. Okay. But it will go up to and include hash tables. And to ease your conscience, to ease it a bit. Typically typically the average on this exam is somewhere between an 87 and a 90. That is the average score.
Cool.
Students have a very good, if you've toughed it out this long, then generally students are able to deal with this stuff. It's a lot more theory. We do have a pretty nice coding question. There are 3 coding questions. Two separate, sorry. I have 1 coding question with 2 parts so it's technically 2 questions for trees, and then 1 question on hash tables, which you should already know what it is before you sit down for the exam. Okay. Now so we'll get into that. So these will be relevant for the exam, and then 11 through 14 which is how you deal with collisions, that will be relevant for the final exam, which I will, don't worry, get to in due course. But you'll definitely want to watch these. These and the how to build it will just help you like understand how these things work much, much better and why they're constant time operations. Because it feels like cheating to use a hash table. But let me emphasize, put this in much more concrete terms for y'all. Interviews generally have, these are very powerful tools for doing, for basically solving interviewing questions that you might encounter when you're going for one of those big companies like Facebook, Apple, Netflix, Google, Microsoft. If you're doing any kind of practical programming, hash tables are a great data structure to think, okay, should I use this one? And look at that first. All right, so I'm going to split you up into breakout rooms to either get started on this or to work on something else or to demo stuff. Actually, if you want to demo something, you can stay here. But I'm going to go ahead and create breakout rooms for you guys. Okay. So if you want to work, go to a breakout room. If you want to demo, stay right here. Let's see. I'm going to go ahead and create 7 breakout rooms. Boom. And open all rooms. Stop recording.